This is the fourth year of our monthly webinars. We have covered a very broad range of electrification topics. They are all online. I will send the index upon request to whoever wants to see what each of the webinars are. There's probably 40 or so. So tonight we're very pleased to have guest speaker Ted Borer, who's president of Borer Energy Engineering. Ted retired this year as Princeton University Energy Plant Director, where he was responsible for heating, cooling, and electrification, and I'm not quite sure what all. But most importantly for tonight's talk is Ted's going to describe Princeton's plan to not only upgrade their 100-plus-year-old physical plant. I think I saw 130 years and something about Princeton. But more importantly for tonight's talk is Ted's going to describe Princeton's plan to not only upgrade the plant, but transform Princeton to reach net zero carbon emissions. This is beneficial to Princeton, but more importantly, sets an example for others to follow. So to help you personally, the last portion of Ted's talk will help you get started on personal steps to similarly reduce your carbon pollution. Ted, that introduction doesn't do you justice. You've done a lot. I will now let you have the floor.
Steve, thanks so much, and I really appreciate the invitation. This hopefully will be not only informative, but a fun conversation. What Steve and I talked about is if you have a question because I've gotten too nerdy and you need me to slow down and say, hey, what did you just mean by that? Please interrupt. Ask me on the fly in real time. If you have a question where you would like me to get into more detail, or you have sort of a tangential question where you'd like to follow a thread that I just brought up, hold that to the end, and then Steve's going to try to moderate those questions. The path that I think we're going to take this evening is going to be, we'll talk at first about the energy that Princeton gets from the central energy plant. I really love that Steve said provides heat and power and cooling. He didn't say provides steam, hot water, chilled water, because the goal is to provide heating and cooling. It's not how we do it, and how we do it is transitioning. And to the point of this whole series that you guys are enjoying, we're moving from a combustion-based energy system delivery away from combustion-based. And you know, why that? Because we've been burning stuff really since the 1740s, firewood, then coal, then natural gas, and now natural gas, a little bit of diesel fuel. But all of this is contributing to climate change. And we absolutely need to stop and frankly reverse that. How do we do that? We need to stop burning stuff in simplest terms. But if you want to really be nuanced about it, I fully expect to have a little bit of combustion almost indefinitely. And we can talk about when that would occur, how much that would occur. And frankly, it's going to be a very minimal, de minimis impact on Princeton's carbon footprint. The second half of the talk will really be, you can't just let this information wash over you. This is a participatory game. So there's work in it to be done for each of us. If you're not a power engineer, or you're not a mechanical engineer, that's not a problem. There's lots that you can do in your own life. And I would challenge you to do as many of the things we talk about as possible. So now I'm going to pull up the slides, if we're okay with that approach, and we'll launch into the formal presentation. So now you should see PowerPoint, and let's get it to the, you should be seeing a pretty presentation mode, right? So
Yes,
title.
this is full slide.
Very good. And you'll get copies of these, as he said. I'll send a .pdf probably next week. Here's the problem on my desk, and it's on many of your desks as each of you are working towards better environmental stewardship. We need to reduce our carbon dioxide footprint. And we can't just do it magically. And most people aren't going to do it by throwing a whole lot of money at something that doesn't give them a payback. Frankly, it has to be good business sense for us to make a difference. Um, so we have to have good financial stewardship. We cannot, take down perfectly good and sacred buildings to the campus, sacred buildings to the nation, just because they're inefficient. We need to work with the existing ones. There are limits on space. I can't. Typically, when you put something way more efficient in and you remove something less efficient, the new thing's going to take up more space. And we can expand on that later. But the more efficient generally means more surface area, means more volume, means it takes up more space. Well, the basement, the mechanical rooms, the attics, the penthouses are limited in space. We have to save the planet today. I don't feel like we have time to waste. So I pretty much have to buy things out of the catalog. And when there's 16,000 people involved, I can't be beta testing stuff on that scale. I can try things around the edges, but not things that would affect the reliability or quality of energy, heating and cooling power that the entire campus community gets. I need to follow the law. We can't make stuff up. I can't interrupt the core business. Providing energy is not core business. We are a support function. And so I need to let the education and research go on. I can't be standing on Sylvia's desk or interrupting Nicholas's or Jacob's research. I have to let that go on and sort of dance around the edge while modifying the building. So effectively, we do have to change the wheels of the bus while we're going down the highway at full speed. I'm not going to expand too much on the concepts of additionality right now. Replicability means that ideally, and Steve kind of alluded to this in the beginning, Princeton wants to be a leader and wants to have others be able to follow the example of Princeton. So if we do something that is entirely unique and nobody else could do it, it really doesn't help save the planet much. It just does something that makes Princeton feel good. We also tend to have fairly high maintenance customers, frankly. So they don't like to go. I can't just tell you, hey, Nancy, put on like 2 more sweaters. Steve, don't be wearing a t-shirt and shorts in January 1st. I need to still provide a warm building in the winter and a cool building in the summer. And I can't do things that are unreliable. It has to actually have some reliability and resilience. So at Princeton, there's 180 buildings. It's a community. There's pretty much one of everything except a hospital for people or a true medical facility for people. So we have research, we have athletic, academic, residential space. There's a little bit of light commercial space. Somebody shout out, what is the most energy intense type of building on that list? Think about it. What's the most energy intense per square foot on that list?
Anybody can unmute.
Maybe residential.
So interestingly, Sue, I think that's a good guess because the students spend a lot of time in the dorms. Nice. Whoever said that, you get the sticker. So in our house, I can show you a handful of places where air leaves the house. The kitchen exhaust, the bathroom exhaust, maybe the chimney if you've got a fireplace, or maybe a exhaust stack if you've got a combustion-based boiler or a hot water heater. But there's not really a forced air intake. If you have a research laboratory, there may be 3 or 4 openings as big as your garage door with a fan that just barely fits inside that opening and blows air continuously through the laboratory, and 3 or 4 more openings on the other side of the building that have similar fans that are that same size as your garage door, and those fans are going continuously. And we might change the entire volume of air in the building 6 times, some research labs even as much as 10 times an hour, because maybe somebody's working with really highly toxic chemicals. And so we don't want the laboratory next door to be sick. And the other thing is maybe somebody's working with super high precision chemistry or physics, and they can't tolerate impurities from down the hall. So it's a once through air cycle, whereas in our houses, the academic buildings, the administrative, the air circulates and circulates many times before it might exit through the cracks around the windows and doors. But it's you each had good thoughts about that. So there's about 180 buildings and there's about 10 million square feet. Your house might be a couple thousand square feet. This is 10 million square feet. Ignore the numbers. They're not really the important thing. The important thing is that today we're running a gas turbine. It's a jet engine. It happens to be the jet engine off the stealth fighter, or my friend Nancy is actually a Blue Angels pilot. So she's got two of these engines. And she's sitting in a very lightweight airframe with maybe a lot of weapons strapped to it, but she's flying through the air at Mach 2 with these two of these engines. So she can go twice the speed of sound. And there's one of her going very fast through the air. Instead, we take one of those engines and we strap it down to the ground, and we can make all the heat and all the power that 16,000 people need on a day like today. So this is not to disparage the military application, because we need that. But the important thing is that flying through the air in an airplane, so we've got people and stuff in a metal tube in the air. Yes, we can do it, but it is excruciatingly expensive from an energy standpoint to do that. So whenever you can avoid flying, do that. If you have to fly, do that, but consider it a precious resource, not a easily expendable or appropriate to expend resource. We heat the campus today mostly with steam. And as Steve mentioned in the beginning, some of the oldest steam pipes go back to 1906. The Princeton steam system was initiated in the 1860s, and Princeton was co-generating by the 1890s, once Edison and his team up in New York City did their work. And I imagine my peers back in the 1890s said, hey, did you hear what the guys are doing up in New York City at Pearl Street? They're like generating electricity. Maybe we should go and investigate that, and we could bring that to Princeton and not have gas lamps in our dormitory rooms. That seems like maybe we could make it safer for them. So I picture my peers, a century and a half ago, doing exactly that. So they were co-generating then, but they were burning coal and making steam and then running a back pressure steam turbine and then using the exhaust steam to heat buildings. In our case, we use the jet engine exhaust, which is 1800 Fahrenheit, and that's plenty hot enough to boil water, and we can make lots and lots of steam. And we've been doing that, like I said, for a century and a half. Making steam to heat the campus for a century and a half. And the oldest pipes were 1906. So you can picture the people who installed the steam lines that are supplying heat to Nassau Hall today, this evening. The people who installed those pipes didn't know the First World War was going to happen. So it was quite a while ago. The third thing came in the 1960s, when as a nation, we began to air condition public spaces. Really, Mr. Carrier didn't invent refrigeration or air conditioning, but he refined the cycle to the point where it was cost effective and where it could be used in public spaces. So by the early 1960s, Princeton University began to air condition the campus. The university was already running boilers and making steam and good at it and reliable at it. So all the original chillers and cooling equipment and even the pumps were all steam driven. We've sold off most of that, but there are still a couple of chillers that date from 1964 and 1967 that are in use today. So Princeton tends to be a very good steward of their installed assets. But on my watch, and actually since the 1970s, Princeton has been installing electric driven chillers to produce chilled water. A chiller is like an air conditioner, is like a refrigerator. They take heat out of one place and they move heat to another place. Has your group, Steve, talked about heat pumps and what they do?
We talked about it. Oh, definitely.
So I don't need to describe what the refrigeration cycle does. It moves heat from one place to another, and it's very, very efficient. So that's what the chillers do. But in the case of the chillers for the university, they all throw away the heat with cooling towers. Now we realize that's a precious resource that we could take great advantage of. We also have energy storage. It's functionally equivalent to 40 megawatt hours, 40 million watt hours, but it's a big bucket of water. It's a big steel tank about 75 feet across and about 80 feet high. And it's got 2.6 million gallons of water in it. And if I cool it way down, I can store a huge amount of energy, the equivalent of 40 megawatt hours worth of electricity, but I'm storing it as thermal energy. The round trip efficiency is way, way better with thermal storage than it is with electric storage. So I would argue that if you ultimately want a heating or a cooling thing to happen at the end of your process, don't store energy as electricity, store it as thermal energy, either hot water or cold water primarily. Here's a little cartoon of the cogeneration system. On the left-hand side, you've got the jet engine spinning a power turbine that spins an electric generator on the right. And if we drew a circle just around or an ellipse around the top line here, it would be about 34% efficient. So 34% of the fuel energy that comes in to the gas turbine is going to leave on the right-hand side as useful electricity. And on the stealth fighter or the F-18 or the Blue Angels, the balance, maybe 66% of the energy is just going to leave the aft end of the gas turbine as heat. It will just heat up the sky. In our case, we're going to take that hot exhaust that leaves the aft end of the power turbine. We'll run it through a catalytic converter like on your car, but a little bigger. And it's going to go through a boiler, and that 1385 degree heat is going to heat up water to make steam. We're still going to have the combustion products going up the stack. Here's a picture of our cute little jet engine. As I said, there's two of those on the military fighter applications. It's maybe 8 feet long, 10 feet long, and maybe 4 or 5 feet in diameter. It's not huge, but it's very, very responsive. Talk about energy storage a little bit. Energy storage does two really important things. Energy storage decouples the moment of production from the moment of use. So the battery you take in the flashlight when you go camping, or even the potato, decouples the moment of energy production from the energy use, and it decouples the rate of energy production from the rate of energy use. So now when I've got thermal storage between my chiller and the campus on the right-hand side, I can run the chiller anytime I want, and I can store energy in the tank anytime I want, and I can remove energy from the tank anytime I want, which is different, or it doesn't have to be at the same moment that I'm running my chiller. So when would I like to run the chiller? I'd like to run it at night when commercial and industrial level electricity is very, very cheap. I might be able to buy it for 2 cents a kWh. And for reference, our electricity at home is maybe 16 cents a kWh. So I'm buying it for 1/8 the price that the resident would pay in the middle of the night when almost nobody wants it. And the power grid is very lightly loaded, and all the equipment and even the distribution system is working way more efficiently. When would I like to use it? Well, I'm going to use this cold water. I'm going to cool the water off really to 31 Fahrenheit, just below the normal freezing temperature. And we have a little nitrate, so it really won't freeze. But then I will pump it out to the campus. When would I like to do that? I'd like to do that when power is extremely expensive, when the grid is heavily loaded, when everything is stressed, and it would be very difficult or stressful for the grid to buy electricity. And I can avoid maybe 25-cent electricity at the peak of the day for commercial or industrial prices. So I can buy super cheap and I can avoid super expensive. And if the power goes out and the chiller trips, I can continue to be reliable. I just need to keep pumping water through the tank. I don't need this heavy industrial chiller and cooling tower to be operating. But on the left-hand side, before this moment, we've called that thing a cooling tower, and you know it evaporates water to reject heat. But henceforth, after this talk, what you owe me, you'll never call that a cooling tower again. I don't want you to. I want you to call that an energy throwaway machine, because really that's what it does. And so what we like to do, instead of throwing away that heat, we have too much heat in the summer, we'd really like that heat, we just don't want it now. So let's find a way to capture that heat and reuse it when we'd like it. And that's the puzzle that we've wrestled with at Princeton. And we have I think, a fairly elegant solution that's becoming more and more common. So here's a picture of our tank. I gave it the wrong numbers. It's 80 feet in diameter and about 70 feet high. It looks like it's 50 feet high, but it goes another 20 feet into the ground. This shows the steam lines, the red ones. Like I said, the district steam system is really from 1906. The red ones are very old. The piping integrity is okay, but the insulation has almost entirely fallen off. So it's very inefficient, even though it still is holding together. The yellow ones don't need immediate replacement, but they will within, say, 30, 40, 50 years. When we build a utility system, wires or pipes, we try to design for 50 years and we try to maintain that system for 100. So we really think in terms of a century. The red is well beyond their design life, and the orange is coming up on its design life. So there's three things that triangulate to the idea that we really need to change something at Princeton. The first being we have aging infrastructure. The stuff's really old and really ought to be either completely redone or replaced. The second is the institution is growing linearly in terms of students, but geometrically in terms of research. And the research, as we already said, is by far the most energy intense part of the business. So we need to add more infrastructure. We need to do it to support a ton more research. And we've got a lot of old stuff. And the third thing is the university is committed to getting to carbon neutrality even before we knew exactly how to do that. So all three of these triangulate to say we really need to move away from steam, away from combustion, towards a non-combustion solution that is way more thermally efficient as well. What you're seeing in this graph is us tracking our carbon footprint from 1990 all the way through a couple years ago. The blue of any color, light blue or dark blue, is liquid fuel, number 6 oil or diesel fuel. The red is gasoline, which you see, even if we eliminated it, it's not really that important for Princeton. Although in your life and in my life, our gasoline consumption is a higher proportion of what we do as individual consumers. The yellow is the carbon footprint associated with natural gas we burned on campus, and the green is the carbon footprint associated with electricity that PSEG produced for us. So stuff they burnt on our behalf. What you see is an upward trend till early 2000s, and starting about 2007, our peak year, we worked harder and harder to get that down, even as the campus grew. And now we've committed to getting it to carbon neutrality by 2046, the 300th anniversary of the institution. And we also acknowledge we can't just do nothing, and then hope magic happens in the last year. We need to follow more or less a linear slope from today down to 2046. But the reality is it won't be a linear progression. It will be a stair step. We'll do a project, there'll be a huge step downward, and then it'll be a few years and we'll do another project and step downward and so on. But the plan is there and it exists and we know how. to get to carbon neutrality by 2046. What are we going to do? We're going to tighten up all the buildings on campus. So basically your building envelope, sometimes tighter windows, definitely insulation, new buildings. You may or may not know the graduate apartment complex over on Washington Road on the Lakeside or Meadows campus is built to passive house standards. And I imagine your group has talked about passive house standards before. So they're super, super tight, but also very comfortable and reliable buildings. We're going to replace the district steam system with district hot water. And in really simple terms, you can understand why that's more efficient. First, brand new versus brand new. Steam, if it's 450 degrees Fahrenheit, will lose a lot more heat to the ground than hot water, which might be 120 degrees. As we get closer and closer to ground temperature, there's simply less heat loss, even if both are brand new and well insulated. But the technology of even the insulation is very, very different, from 150 years ago than it is today, where it's directly buried. There's no way for the insulation to fall off. It's factory insulated and it's very tough insulation skin. The next thing is we create an electric powered heat pump facility, a lot like you might build for your house, except much, much bigger. We're going to take heat out of the things that deliver heat, computers, lasers, electron microscopes, CT scan machines, all produce heat all year. And then we're going to deliver heat, ideally, to people who are taking showers or washing dishes or using it for research needs, or in the winter, using that heat for heating the buildings. And then we'll create a way to store on a daily basis, which is really more of an economic play. So I can buy more and more electricity in the middle of the night when it's cheap, produce all my thermal energy for the next day, and then deliver that thermal energy when electricity is expensive. I'll create seasonal storage, and that's the geoexchange that I'm sure you've heard about. So we'll store heat from a whole summer, and we'll jam it in the ground, and we'll use 50 billion pounds of rock as the energy storage media. We'll slightly heat it up, and then in the winter, we can extract the heat from that rock and deliver it back to the campus, instead of having thrown the heat away with a cooling tower and then having to burn more stuff so that we can deliver heat. We'll also install whatever we can in terms of solar. We won't, even if we coat the whole campus, meet the whole campus's needs. So we'll end up having to buy some offsite power, renewable power. So this is what we're doing today. On the right-hand side, we're burning stuff. We're delivering heat in the form of steam to campus, and we're getting back warm water to the boiler, which we reboil and make more steam. On the left-hand side, I am also adding energy to this system to cool the campus, to remove heat from the campus, and then throw that heat away through the cooling tower. So you see on the right, I'm adding energy to the whole system and delivering heat to the campus. And on the left, I'm using yet more energy to remove heat from the campus from things that need cooling, and I'm throwing that heat away. So that feels fairly inefficient. Instead, what we'll do is we'll modify the system. We'll get rid of the boiler with the combustion. We'll get rid of the chiller and the cooling tower, and we'll put a heat pump in their place. And so now I can pull heat out of the heat producing things, the lasers, electron microscopes, CT scan machines, computers, and I can deliver heat to the showers, the sinks, the dishwashers, the other things that need heat on campus. And the imbalanced part I can store in the form of hot water, in the form of cold water, or I can put heat into the geoexchange. So in this case, the geoexchange is not directly connected to the buildings. The geoexchange is connected to the energy plant, which then uses it as a form of energy storage. If we were working on your campus, your airport, your hospital, your military base, this is the first thing I would ask for is maybe 3 years worth of data showing every hour, if we could, how much heat are you adding, how much heat are you removing? And what you see is Princeton University in the summer removes a whole lot of heat, and in the winter, the red delivers a lot of heat. And the graphs look about the same, the amount of heat added is a little bit more than the amount of heat removed in the summer, the blue. But if I make my steam system into a more efficient hot water system, those graphs, winter and summer, heating and cooling, are going to be really similar in size. So what I need to do is run the heat pump simultaneously to take any heat I need out of the things that need heat removal all the time and deliver to the things that need heat delivery all the time, and then capture the heat from the summer and deliver it in the winter using geoexchange. Left-hand side is a picture of the drilling rig. So far, the university's put in about 1,000 geoexchange wells. They go down 850 feet, so about 300 meters. On the right-hand side is an industrial chiller. Functionally, it's the same as your refrigerator. It's the same as an air conditioner. It takes heat from one side and puts it onto the other side. But this is hooked up to thermal storage and geoexchange. It is not hooked up to a cooling tower. This gives you an example of the size pipe. So I'm going to drill a 6-inch hole in the ground, go 850 feet down, and I'm going to take this pipe and have it fabricated in the shape of like a U, soda straw. Goes down, goes around a 90-degree bend, comes back up. We stuff it 850 feet in the ground, and then we fill that all up with, we fill the outside of the pipe and the inside of the hole I drilled with grout. So it's basically a super tough pipe in concrete, in rock. I fully expect it'll be there a century from today, still functional and working just fine. It's designed specifically for this application. This is a rendering. If you've been on, not Faculty Road, if you've been on Fitzrandolph Road, across from the stadium parking, you'll actually see the heat pump plant on the left and the thermal storage tanks. The cold one is closer to us, and just beyond the trees between the front tank and the plant, you can see the hot thermal storage tank. The cold storage temperature is about 41 degrees Fahrenheit, well less than you would want your office to be on a hot sunny day. And the hot one is about 120 degrees, a little bit hotter than you would want your office or your shower. So, or maybe even 140 degrees. So we have a little bit of thermal leverage or potential energy that can be lost in the transition from the tanks or the heat pump plant all the way out to the buildings. This just is iconic of us decorating the whole campus with solar PV. Some of the controls and what you're looking at is we're very, very data intense. We're very, very data driven. So you can see the thermal storage tank. We're measuring the temperature top to bottom and the temperature top to bottom and all the operations of the chillers. Also the temperature of the geoexchange fields all the way down 850 feet in each one of the geoexchange fields or under the parking deck or the soccer field. I'm going to skip this, but just suffice it to say, by moving to this, we save a huge amount of electricity. We save a significant amount of energy. We save a lot of CO2. And by not running cooling towers, we avoid 50 to 80 million gallons of evaporated potable water each year. So if we were doing this project in Baja California, or if in New Mexico, or in Atlanta or Arizona, we would do the same project, but we would be celebrating how much water we were saving. And oh, incidentally, we saved a lot of money and we saved a lot of carbon footprint. So the technology is very much a water saving as well as an energy saving technology with the heat pumps and geoexchange and thermal storage. All right, so let's make it actionable for you. You get this list. I'm not going to read down it. You can faster than I could say it. Just scan down that list briefly, and then I'll dig into a little bit more detail. So at home, you can put solar PV on your roof, or you could purchase community solar energy. At home, and this is a picture of Princeton where we're digging 1,000 wells. For your house, you probably only need one, maybe two wells for your geoexchange. And they wouldn't have to be 850 feet deep. They might be 400 or 500 feet deep. And that would be enough for most of our houses. If you have an extraordinarily large house, you might have 3 or maybe 4 wells, but probably not. At my house, we also not only have solar electric, but on the top left, you can see solar hot water. I did that long before the price of solar PV came down. I probably wouldn't do that today. I would put more solar PV today. And on the bottom, what we did is we put a heat pump hot water heater. So any hot water that I produce that's not quite hot enough to take a shower in, the heat pump hot water heater will supplement that. But the problem with solar hot water, one problem with solar hot water, if I have an excess, say I go away for a week and I have an excess of heat in August, it just gets wasted. It doesn't go anywhere. But if I had solar panels there, that excess energy would go into the grid. I'd sell it into the grid, and then I could receive it back later for an energy credit. So I'd rather, and price-wise, it makes more sense, and there's less stuff to break, and I'm not playing with water and that kind of thing on my roof. You can use heat pumps, obviously, instead of combustion. Just like we're doing at the university on a large scale, you can do, and what you can see is the left-hand side is a heat pump for heating and cooling our main house. And on the right-hand side, you see what's called a mini split that just cools the office. It's about a 200 square foot office that the mini split heats and cools very, very efficiently. Here's another technology you could use. When you are standing in the shower, the water feels comfortable. The water cascading off your feet does not feel cold. It's probably warmer than body temperature. So if you're 98.6, the water spilling down the drain is easily 100 degrees. So you're wasting a lot of heat. Where's that go? It heats up the front lawn. So what I did is I bought this device, which takes the cold water supply pipe to the bathroom. It wraps that pipe around the soil line, the drain line that comes out of the shower. And then what happens is when hot water comes off the shower drain, it heats up the cold water going up to the shower. There's no valves, there's nothing to break. This is going to last as long as all the rest of the plumbing in the house with really nothing to fail. But what happens, as long as there's only one person in the bathroom, when the heat goes down the drain, the cold water line brings warmer water in, and I don't need to use as much hot. If, say, Steve came in and brushed his teeth while I'm taking a shower, he might get some warm water. And so we would have to plumb things differently if we're having a group bathroom like a dormitory versus a single person bathroom like in most of our houses. I have a few friends who call me up when a tree falls in their yard. They say, do you want it? I say, if it's hardwood, I'll come cut it up. I will split it at my house and I'll clean up your yard. I only want it from Hopewell Township or certainly Mercer County, but really only a few miles. So I'm not transporting bugs around the township. And this would already turn into, it would release methane, or it would release CO2 in its degradation. So it's fairly de minimis impact by burning it to reduce the amount of energy I need for heating the house. But I will fully acknowledge there's still particulates and there's other combustion products that really long-term we don't want. In terms of transportation, fairly obvious, a hybrid, a bicycle using your own feet, a bus, a train, anything but single person, single driver, internal combustion engine, and obviously EVs aren't shown here, but that's the way to move eventually. In terms of food, growing your own food is very helpful. You're not transporting it, you're not packaging it, you're not paying for marketing, you're not paying for the advertising or the putting it out, or even the refrigeration that goes in the market. So you're getting fresher food that you know exactly the provenance, you know exactly where it came from and how it was treated, and ideally it's organic and that kind of thing. You want to ideally follow as much of a whole food, plant-based diet as possible. Yeah, it's going to keep you healthier, but it's also, animals are fairly inefficient converters of plant material or flesh that they eat. They're fairly inefficient at converting that to useful calories that you would eat. So classically, it's going to take about 10 times as much land to raise food for an animal than you would eat, compared to the same amount of food that you would grow. Obviously, you're going to grow a different type of food for yourself than you might feed the animal, but it's going to take about 1/10 of the land than if you ate animal food for your calories, and about 1/10 of the water, and about 1/10 of the phosphorus and nitrates and things like that you would put onto the land and then might work into the aquifer as runoff. So there's layers and layers and layers, as well as compassion, of reasons why, but purely the more you step towards, I'm not being an absolutist, but the more you step towards a whole food plant-based diet, you're going to also reduce your environmental footprint and reduce packaging and transportation. Ideally, you're going to grow even more than you need at that moment, just like thermal storage, just like batteries. You're going to preserve the harvest, and so you can have some of what you grew excess of in the summer, you'll have in the winter. Very, very much like our geoexchange. At our house, we also have a couple of hens. It's not a huge flock. They produce two useful things. Well, they're delightful, but they also produce eggs, which some of the people in our house eat, and we use some in cooking, but also they produce chicken poo, which in my mind is at least as valuable as the eggs. So it's very high nitrogen. The chicken poo then and the chicken bedding goes into the compost. The compost feeds the plants feed me. I cut the scraps off the ends of the plants that I eat and I give it to the chickens. And I really wanted our children to see this entire cycle, that if you do it right, you can have this little tiny circular economy in your own backyard that goes round and round and round and nourishes the land, because we're not doing one thing super intensely. We're doing a whole lot of little steps. And the compost, to do it right, if you have the right mixture of nitrogen and carbon, which isn't hard, and the right amount of water and air, your compost is going to cook at about 160 degrees Fahrenheit, 160. So it will kill most of the bacteria and certainly all the plant seeds if you do it right. In terms of water, my overall message is don't transport water. Get it out of your tap or get it out of the ground, but don't transport it in trucks and bottles if you possibly can. You're going to capture it off the roof and fill up a tank for gardening, perhaps. You are not going to buy bottled water or soda. Take water out of the tap and carbonate it yourself at home. And you're avoiding the truck and the transportation and the road clutter and all that, and the bottles, the waste. Don't transport water in terms of your beans and things like that. Buy dried beans. They weigh less per calorie if you want. There's much less packaging in these little plastic bags than in the metal cans. And then you're going to rehydrate it and cook it at home in a Instant Pot or something like that. One last point in terms of meat production, meat consumption. If you completely eliminated all your use of water for toothbrushing, showering, bathing, toilets, washing the clothes, dishwasher, meat production, I'm not saying reducing, I'm saying you never did any of these activities again, you wouldn't make nearly as big a difference in water use as if you reduced your meat consumption by the equivalent of 4 ounces of beef a day. It doesn't have to be beef. It could be the chicken equivalent or the fish equivalent. And yes, there's slight differences in terms of whether it's pasture raised or farmed, but the more important is there's so much water used in capturing these things, cleaning these things, processing them, transporting them. Your meat consumption, again, I'm not being absolutist saying you must eliminate meat consumption. I'm just saying by reducing it, you can maybe a factor of 3 to 1 avoid water use, as well as phosphates and nitrates and things you don't want on the land, as well as land use. You can eclipse the effect than if you reduced your toothbrushing or took a shorter shower, took a shorter bath, or that kind of thing. So it's very, very impactful, and most people don't realize how impactful to simply reduce your total meat consumption. And I would like to land it there. And you may just say, I have heard enough from you, Ted, I'm done. Or you might have some questions, and I'm happy to work with either one.
Sue Dorward had an interesting question in chat. She said, say the climate warms and you end up with having more heat than you need to store. How would you release the excess heat since there is no cooling tower?
So that is a super important point, Sue. And the cooling towers still work. Princeton still owns the cooling towers. But I don't want to barely ever use them if I don't have to. But that's in our back pocket. We still could if we have an imbalance. I'm not expecting to never need any heat. But if we move from a place where the university needs a little more heat and a little less cooling in the year, and we move from a place where we need more cooling and less heat, we would reject heat. The imbalance through a cooling tower, maybe through geoexchange, if that were much larger than our needs. We know what we've built. We know what we've designed for. We don't know how much heat the aquifer will take away from us. So it could be that the aquifer itself will take care of those needs. But you're asking a really important design question, and one that I hope to be part of reporting the answer for over the next several years. What you're asking is a deeply important question.
Another question about thermal storage. Do you maintain a temperature gradient in your thermal storage tanks? And if so, how do you do that?
Yes, it's amazing how stratified this is. An interesting thing, you might realize, like water, as it gets colder and colder, it gets denser and denser until about 39 Fahrenheit. And you probably didn't remember that number, but then it actually gets slightly less dense. That's why ice floats on the pond. It doesn't sink to the bottom of the pond. It's not the most dense thing. But by adding a little bit of nitrite and a little bit of nitrate to this tank, which always remains full, that causes the density to be depressed of the entire thing. So we end up having a stratified thermal storage tank. So I can have 50 feet of 31-degree water. There might be 3 or 5 feet of anything else. And then the rest of the top of the tank is 56 degrees. And it's amazing what we call the thermocline. Anything that's between the hot temperature and the cold temperature might only be 3 or 4 feet thick. If we introduce the water gently and remove the water gently from the tank, and by that, I mean the tank has been designed, we can move 10,000 gallons a minute through that tank and we still won't stir it up. So it's very carefully designed how you bring it in and out. But yes, it's thermally stratified. Same thing with a hot tank, but that's easier.
That's the last question in chat. You might ask, just open it up for any questions from anybody.
Hi, Steve.
Everybody's free to unmute.
Hi, Steve. This is Darshana.
Hi.
Hi, Darshana.
Hi. So I have a question. Thank you. Great presentation. My question is, when we take shower, when we go to take shower, first few minutes, we just let water run, and that water goes to waste, and that bothers me a lot for many, many years. Is there any technology or any invention or anything that you guys come up with that how to save that water or store water or repurpose that water before we actually take shower?
So I have multiple layers of answer, right, Darshana? I don't know if this passes health code, all right? So I don't want to tell you to do this, but you could put a diverter valve so that the laundry and the shower water goes out and you could water the lawn. You could take care of your plants with it and that kind of thing. But you definitely don't want the entire bathroom drain. You don't want to be putting, human waste on the lawn. That would be very, very unsafe. So you'd have to be very thoughtful about how you plumbed it so that the sink drain, and then you'd also have to be more thoughtful about you only use organic, like I'll say Dr. Bronner's or something like that, soap that would not be negative to the environment. You don't want to be introducing phosphates and nitrates and things like that. So can you? Yes. Would it take a little bit more sophisticated plumbing and a bunch of thought? Yes. So I don't know if we could do it in a cost-effective way. I know we could do it. All right. So it's a very nuanced answer for you. And it would maybe depend even on your lifestyle and your house, how much you were willing to modify it. There's
I
not an
know,
easy.
but this is like ongoing problem. Water is getting less and less everywhere. I live in Texas. I was in New Jersey and now in Texas. So this problem, I'm a climate activist, scientist, so this thing is bothering me, and I said nobody's trying to find this solution about this thing or working on this thing. It's just going out of the,
So
yeah.
if you remember that pie chart I put up, I would keep taking the same shower you do, knowing that some of that water is going to be wasted. And instead, I would cut back by 4 ounces or the equivalent of 4 ounces of beef a day. And you will make a much bigger difference than if you didn't take the shower, at all.
I don't eat meat, so I don't have to worry about that.
All right, so the
I have a
animals
good
thank you and I
solution.
thank you. All right, well, so you install heat pumps and you don't evaporate water through cooling towers. I don't have an elegant solution for you. I have a really messy solution for you so far.
Yeah, so okay, one more question, please. So all these beautiful things that Princeton came up with thing, is this a collaboration with other universities, high-end universities like Ivy Leagues, or this is from European technology? How or your scientists come up with all these solutions, all these years that you've been working on? Where is it coming from, all this thing?
So there's places in Western Europe that are more advanced than us. I attend and participate very actively in a group called the International District Energy Association. And these people gather from all over the world. We had a conference a week and a half ago, and we have one in February. And this is where I think the most advanced thought in the world on these topics is. This is where I think the most expert people, but this is absolutely not something that was unique at Princeton. Princeton does tend to be the leader in this, so we're sort of the largest and the furthest ahead and the best well known, especially because we've done all of these things together, where some of our peers, Stanford has done the heat pump and they did thermal storage, but they didn't do geoexchange because they're a different climate than us, right? In Texas, we would have a very different balance of energy needs. So my peers down there at UT Austin have done slightly different things, and they're not quite as far ahead as we are. There's places in Western Europe that are further ahead, but they might be on a smaller scale. So at this moment in time, we're among the leaders, but it's not because we're advanced thinkers more than any of our peers. We're just a little further down the path.
Thank you. That is
Yep.
useful. Thank you.
To Darshana's question, though, almost all of us, when I say us, the pharmaceuticals, military bases, airports, hospitals, universities, behind the scenes, we all have very similar energy plants. And almost all of my peers are somewhere on the continuum from having a completely combustion-based steam heat delivery to having a non-combustion based hot water heat delivery. Princeton is a little further on that path, but almost all of my peers around the country, many around the world, are somewhere on that continuum.
I would definitely imagine that thing that I'm just curious that who is doing what. I'm always curious what is Harvard doing, what is Yale doing, what is Princeton doing on in this thing. So yeah, it's
Yale did a bunch of geoexchange before we did, but they did what we'll call open loop. So they were exposed to the aquifer. Some of their geoexchange wells silted up. So as a deep pocket, I'd be anxious about Princeton doing open loop technology, but it's way more efficient. So if you have the right type of rock, that might be the way to go. I will say, when I send Steve the PDF, my email's on the front. You know, I'm running a little business, but if you have a simple question, who do I talk to about this? Shoot me an email. I want to be helpful.
great. I would love to. Thank you, Doctor.
There's another
What else?
question in chat, maybe quick. Are heat pump water heaters the most environmentally friendly way to heat water at this time?
That's a hard question, right? I mean, environmentally friendly. A friend of mine gave me a little tiny solar hot water heater that's only a single evacuated tube, and I can boil a few ounces of water in it with just sunshine, even on a cloudy January day. But it's crazy and efficient. It is very environmentally friendly. The heat pump, I'm not going to pretend there's not materials in it. There's a lot of materials in that. There's a whole refrigeration cycle. I found that penciled the best. It was the best economic and environmental footprint. So I'm not making a single dimensional decision. I'm making a multi-dimensional decision. Is it reliable? Can I get it fixed? Can I get spare parts for it? Is it energy efficient? Does it fit in my house? All of these different layers. I kind of like, if I were just looking at a standard house like you would find in Mercer County or so on, I would expect that the heat pump hot water heater would be a really good choice, but it is very situation specific. How is that for a tap dance as well as sort of an answer?
There were two more questions that may be of interest. Can you
Bring 'em on.
tell us more about or point us to resources about residential thermal storage?
Oh man, well, you actually have two forms in your house already. I'm fairly confident you already have thermal storage in your house. If you open up the freezer, you're storing cold, all right? And I'll demonstrate that with a little thought experiment. If you unplug the freezer and you want the Ben & Jerry's and you unplug the freezer for 4 hours and you say, geez, I'd really like some ice cream. Go ahead, open the freezer, take the ice cream out, close the door. Nothing else is going to melt. Take your ice cream, put the ice cream back in, leave the freezer unplugged for a couple hours, and you can plug it in again. All right. So you already have thermal storage. We're just not exploiting it. Then on the other side, you have a hot water heater, presumably. Most of you don't have an instant hot water heater. Most of you have an electric or a gas-fired hot water heater, and it's got a tank with it. So you have anywhere from 40 to 60 to 120 gallons of water that's pretty darn hot. It's just sitting there. So let's do a thought experiment. We could save a whole lot of stress on the power grid. Let me step back a little bit. The power grid has nuclear power almost all day and all night. The power, that's the cheapest operating thing. It's not the cheapest to build, the cheapest capital cost, but it's the cheapest operating thing. And there's a little bit of hydro at night. There's no solar at night. But during the peak of the day, when everybody wants power, the nuclear plants are still on as your base load, but at least in PJM, New York ISO, many of the other regional transmission operators in the country, the peak of the day is much more polluting than the middle of the night because you're bringing on more and more stuff and you're bringing on the less and less efficient things until the peak of the demand and the hottest, the most expensive part of the day is dinner time, not solar noon. So it's dinner time when Darshana is still at work and she's got the air conditioner on at work, but Steve goes home and he's working on fixing dinner and he's got the air conditioner on there. So you've got both residential and office type and commercial loads. It's dinner time. So then for industrial and commercial consumers, the price is higher at dinner time and lower at breakfast time or the middle of the night. And the pollution follows that same pattern. It's less polluting in the middle of the night. It's more polluting in the peak of day. So let's ask ourselves, how could we motivate people to do a less polluting activity, even if they still want the same shower and the same ice cream and the same computer? Well, yeah, let's talk about thermal loads only. What could you do if I said, if I gave you a time of use electric, so I only charge you 2 cents a kWh in the middle of the night, and I charge you 25 cents more than you're paying today at dinner time. Well, Mary would charge her Tesla in the middle of the night. She wouldn't be charging her Tesla at dinner time, right? Because she'd say, oh, I can buy the same charge of electricity off a nuclear powered grid. Something Tesla's nuclear powered, not combustion powered. All right. And Betsy would say, oh, I could do the laundry in the middle of the night. I want the jeans dry by the time I get up. I don't care when the jeans got dry. Yeah, wrinkly, but I could have the laundry machine do its cycle when it's cheap. I don't have to be doing that at night. What else could you do? Well, your hot water heater. You could heat that up with really cheap and less polluting electricity, and you could avoid heating it up at the most expensive and polluting time of day. The crock pot, the dishwasher, the electric dryer, like the car charging, and we could probably name a dozen things that if you were economically motivated, you could change the time of use without negatively impacting your lifestyle, all right? And you could reduce the amount of pollution on the grid. So I'd argue a really, really important thing to do is to expose the retail consumer to real-time electric rates. So we need to change the tariffs, and that will help save the planet quite seriously. You could also do this voluntarily, but you have no economic motivation to. You will still help avoid pollution by avoiding dinner time power use.
So it's a kind of duty of utility companies to educate consumers.
It's not so much the utility company. We actually need to engage with the Board of Public Utilities. So the people who are responsible for getting the tariff approved. And you also need to work with the consumer advocate so that we're not net charging you more for electricity or charging you less, but the utilities end up compensated the same. The consumers end up, it's a thorny problem, but it is very, very solvable. And it doesn't take any more physical infrastructure. It's just a lot of permissions and a lot of meetings, really. It would take humans acting like grown-ups and actually trying to collaborate. What else would be helpful? What else is of interest?
The idea of health benefits of eating more plant-based foods that was raised by Judy Green. and maybe many others share that same sentiment. I know I'm mostly vegan.
Yeah, me too. Me too. And I got there through very selfish. I would like to be healthier than I am today. And my cardiologist can attest to the success of it. I won't drag you through the story, but it has made a huge difference in my life. Only after changing my diet, I realized, oh, this is completely consistent with the work I do to reduce my environmental footprint. And then there's this third layer, it's compassion for the animals, which I understand that intellectually. I understand that from the neck up. That's not in my heart yet, but I see it. I acknowledge it. And so there's these three different layers. One's totally selfish. I just want to keep myself from dying of heart disease, which is the most common way we as Americans are going to die. And then the second is the environmental impact, and the third is compassion.
I think we've pretty much run out of time. I really want to, I'm sure we could keep going with other questions. It's close to 8:15. I wanted to just mention that Ted spoke about many things that individuals can do to reduce their greenhouse gas pollution. And a little plug for something that we're doing. We have a major push right now to move from fossil fuels to clean electricity. And if you have questions about how to transform your household by electrifying and you lower your overall utility bills, feel free to take advantage of a free coaching service we established last year. It's called the Electrification Coaching Network. We have trained coaches throughout New Jersey. They're free to use. They eagerly await your chance to help you to plan your household electrification in years to come. And I'd like to share, I'll just put on sharing something that will get you there. So this is a QR code you can go to, or go to njecn.substack.com and learn all about it. We've run out of time. I thank you very much for joining us. We have these the third Thursday of every night. Ted, I think you'll find entertaining, and we have another entertaining webinar that's on the third Thursday in July. We have an entertaining talk from a high school teacher who will describe his electrified EV, and he travels extensively with his family during summers. He's going to join us via Starlink right now from his camp out somewhere in the Sierra Nevada mountains. Actually, not now, but in July. So it'll be an entertaining lecture, I'm sure. And Ted, thank you. I really think you did a good job. I think we had a lot of interested people here. Thank you.
Thank you so much.
It was really delightful to talk to you guys.
Thank you.
Thank you.
Very, very proud of Princeton University.
Oh, sweet. Thank you. All right. Peace, my friends.
Thank you.
Bye, everybody.